Hi, greetings everyone. So today we delve into the mysteries of the Van Allen belt, which is a region in the space teeming with very high energy particles and intriguing antimatter. And hence we present to you our mission Paridhi, which is a 6U nanosatellite constellation mission for the observation and the study of the Van Allen belt. Introducing you all to the team, each of us specializing in different subsystems, as you can see. Yes, now speaking about the need of a mission. First of all, speaking that Van Allen belt is a region of intense radiations. These high radiation levels contains energetic particles, which includes electrons and protons, and hence these have the potential to cause serious harm to the vital spacecraft systems, and hence they interfere with the communication networks and in turn threaten astronaut safety. We can also get to know about the mysteries of antimatter, speaking of in detail in the future slides. So our mission is basically a part of a broader scientific communities where we just push the boundaries of space exploration, and we may not aim to solve the mysteries ourselves, but it will act as a foundation for the future space exploration requirements. Now, speaking of the mission objectives, the most difficult part of the Van Allen belt is the South Atlantic anomaly. It is a region where the radiation levels will reach the peak, where it will amplify the risks for both the spacecrafts and the crew. And hence, to address this challenge, we have equipped our satellites with a range of payloads. So, using our payloads, we can measure radiation levels, energy spectrum, and particle fluxes, which will in turn provide us crucial data for assessing what the hazards to spacecrafts are and for the future human missions. Through our mission, we can also understand the correlation between the radiation and antimatter by understanding its interactions and the dynamics in the belt. And speaking of space exploration, by understanding the radiation level and the antimatter confinement in the Van Allen belt, we can improve the spacecraft design by radiation shielding and using advanced materials, and hence it will help these advanced research in particle physics and related domains. Now, moving ahead to individual CubeSat subsystems. In the structure subsystem, we can notice a 6U chassis, which is made up of aluminium 6061. It consists of 4U portion for holding the payloads and the 2U portion for holding all the electronics. It also has an entrance area for the ions, which is used by the MIC8 payload. You can see in the future slides. And for thermal protection, we have the shielding layers and the coatings, which also you will get to know in the future slides. Now, speaking about the mass and volume budget, we have listed down the mass and volume budget of each and every component, as you can see in this table. And in totality, we could estimate the dimensions to come around 4.51 U and the total weight to be around 8.2 kgs, where we have excluded the thermals and the panels. Speaking of thermals, we have to utilize a robust radiation shielding strategy, which is basically using specific materials and a calculated thickness in order to protect the portion of sensitive components, and in order to dissipate the charges that accumulate on the surface of our chassis. We use charge dissipative coatings like Luna XP, and we will also be using multi-layer insulations, which will be maintaining a stable thermal environment throughout the period.
So having an objective that basically boils down to understanding the space weather at the Van Allen region, we understand the charged particles qualities and quantitatively measure the qualities they have. So we use magnetic ion spectrometer, MAG-IS for short, which uses a uniform magnetic field created within it to calculate the momentum and selectively send them to a particular detector, which records their energy level using a current pulse that is generated due to the analog output it has given. And with this, we can understand the momentum as well as the energy from a charged particle. And for all the charged particles we come across, we get these two quantities. So magnetometer instrument is used to measure the magnetic field direction as well as the magnitude at that particular region. And we have given an example of a common off-the-shelf payload which is used in CubeSats. And this is the NSS magnetometer. And all the required specifications of the same is given in the slide.
Okay, now moving on to our secondary payload, that is the retarding potential analyzer. It will basically verify the readings coming from MAG-IS. It is made up of several grids, which will have different potentials for slowing down or speeding up the particles. And one of the grids will have a ramp potential that can help us to selectively collect the ions. We can basically control the amount of energy of the particles that we are receiving. So, and after that, it is captured in a collector, and that basically collects the charges and converts it into a current. And that current is later on converted into a voltage signal using transimpedance amplifiers. Now moving on to RADFET, it is basically our dosimeter. It will calculate the amount of ionizing radiation received by a satellite by monitoring the shift in the threshold voltage, that is the delta VT given here. And it can also calculate the dose rate using the current flowing through it.
Next comes the attitude control subsystem of the satellite. The sensors used for relative positioning are sun sensor with relative to the sun, other sensor with respect to the earth, magnetometer with respect to the magnetic field of the earth, and dosimeter for aligning the satellite with respect to desired radiation patch. The considered actuators for control operations are reaction wheel and magnetotalkers. The both are planned to be designed and built in the ISTS Space Lab.
Yeah, so for communication subsystems, so as we calculated data volume, it was coming around 200 megabits per revolution. And for specific to MEG-IS, it's around 6.2 to 7 MB per orbit, or equivalent to 81 MB for whole day. Yeah, for the given data volume, we calculated downlink budget. So for this, according to our power from the antenna, it's coming around 2.3 dB watt. And detecting the path loss, we are getting the isotropic signal ground station is around minus 160.8 dB watt. And further calculating it, we are getting a threshold of 9.6, and the total link margin we are getting is around 8 dB, which is sufficient to get a successful communication between satellite and ground station. And going further, this is our link budget designed for 2050 megahertz. And similarly, we are getting a ground station EIRP of 44.4 dB, and reducing the path loss and atmospheric losses, we are getting it around minus 24.3 dB. And further, reducing the calculations and providing the EB threshold, we are getting a link margin of around 22.9, which is more than sufficient for getting a proper communication between satellite and ground station. For this given communication system, we have decided this wideband S-band patch antenna. The given below are the features related to its light heritage and the band ranges. It's a dual bandwidth antenna. And next, we are going to the S-band transceiver. So it is also a twice bandwidth and transceiver, which has a transmit frequency of 2200 to 2290 megahertz and a receiving frequency of 2025 to 2110 megahertz. And the given power requirements are given in the given slides.
OBC subsystem. So we are using the two SD cards for 16 GB capacity. Basically, this is a radiation sustained device, so it can sustain in WAN element. So for creating the custom logics, we are using RTX FPGA, and these are the technical specification of it. These are the radiation specification of this. So for processing the 200 megabits of data and for the radiation sustainability, we are using RAD 750 microprocessor, and these are the specification of this hardware. To communicate with other subsystems, we are using some interfaces, like for ADC, we are using RS485, and for EPS, we are using two interfaces, I2C and UART. For communicating with external storage, we are using SPI serial interface, and for the communication, we are using two interfaces, RS232 and UART. And for the MEG-IS and magnetometer, we are using Ethernet 100 base TX, and for the Garrett counter, we are using USB.
So moving on with the orbital mechanics, our constellation is consisting of 4 satellites, from which 2 are in a orbit and the rest 2 are in the another orbit. These are the orbital parameters for both the orbits, from which all are the same other than the right ascension angle. This is the ground track for both the orbits. The perigee is situated at 400 kilometer altitude and the apogee at 2000 kilometer to maximize the interaction time with the Van Allen belt. And doing the calculation, we got the interaction time with the Van Allen belt as 15.5 hours, and the interaction time with the ground station is nearly 2.5 hours. And the orbit is much stable due to atmospheric baggage release here.
Basically, any implementation plan is divided into 3 stages, which is the pre-launch preparations, the launch phase, and the in-orbit operations. The pre-launch preparation will include any design and the testings, which will basically take place in our college in labs like SPACE and our EPDL lab, and also in collaboration with ISRO at their VSSC or LPSC testing facilities. Next comes the launch phase, where we'll be integrating our CubeSats onto the PSLV platform, which is the suitable rocket we'll be using for a launch, and hence choose a suitable launch window in constant communication with ISRO. And while the satellite is in orbit, we will be continuously monitoring the solar panel performance and the degradation of it, and hence assess the communication and tracking of our satellites with the help of our established ground stations. Speaking of an approximate project schedule, it is basically to begin in January 2024. As you can see, a carefully designed flowchart where our design and development will start at around August 2024, and we are expecting our launch by July 2025 after all the testing is succeeded and it is agreed by ISRO. So basically, this is an approximate cost budget for our components used in the satellites. And since MAG-IS and RPA we'll be developing indigenously in our college, hence an approximate price is not given for that. But our goal will be to optimize the cost to a great level.